Okay, we are at weekly update 14. You just finished the first half of the last chapter that you're going to be covering in Calculus 3. So notice a couple announcements this second half, so the last bit of the book, the last part of the chapter here, the challenge problem is optional. So if you want to submit that yourself or with a subgroup from your team or your entire team, that's all optional bonus. And just go ahead and email it directly to me if you did it by yourself and you want me to just extract that part from the Google Doc. Okay, some more details. We talked about this last time with the window for your final exam. This is already next Friday. So Friday the 23rd, it'll open early in the morning on Friday and it'll close Sunday, April 25th, 11:59 p.m. So usual nighttime deadline. So you have that window to allot yourself 2 hours and give yourself a little bit more, maybe a chunk of 3 hours of time during the day. When do you want to take it? You'll go into OAKS. You will start it. It'll look like a giant OAKS quiz. Remember, the first 30 questions are concept questions. They're 1 point each. They should go rather quickly. Places to look to practice those: old quizzes, end of chapter concept reviews. They are pulled directly from there. So make sure you know your vocabulary, your terms, and same style that we've had. Not trying to trick anyone there. And then you'll have 10 to 15 calculation questions. Those are 5 points each of the next part of also in OAKS. So they'll do like 30 concept questions. Number 31, now you need to start doing calculation one, so you have to show your work. So you're going to select a multiple choice as you normally do on a quiz, but you have to write on your paper, show your work, the steps, what you were trying to, if you're doing a double integral, what are you trying to double integrate? If it needs a picture, you're drawing everything right there. Then at the end of the 2 hours, OAKS will cut you off whether you're done or not. Auto submits what you've done thus far, and then you have to submit your pages of work. So those pages of work, however many you have, usually like you do for your homework, submit them as one PDF, and you have 15 minutes after you've completed. So if you started the exam at 1 o'clock on Saturday, it'll cut you off at 3 o'clock. You have till 3:15 to submit your PDF in OAKS with your work. Problems will not be graded unless there's work. Again, it goes beyond me to an assessment committee. And I've warned all my students in all my classes since COVID hit, please don't be tempted to cheat. Show your work. There's some problems, I will say though, that we've been using tech tools throughout. You can use them to get images and pictures. And even if there's somewhere like, what are the ones? Oh, the curvature ones. And what are the other ones that are just nasty integrals? Oh, surface area, right? And so I'll tell you to model it. Please set it up as a double integral and use a tech tool then. So I specifically tell you, please use a tech tool to finish this. You can use those to check your work on other problems as you've been doing throughout the semester, but you have to show your steps of what it was you were trying to do. Because this is going to other folks, and there's particularly in math, most of my colleagues are super concerned about cheating, trying to do everything they can. I've been wanting us to do computer-based math, so we're going to use that as a tool, but don't be tempted to go take that a little too far for the finals. Just show off all that you know. You guys have done great. Okay, calculation question. So there is, maybe I should share the screen here, just to make sure we all know where this is. There is in your OAKS for this class, with the content, there is a module 8 final review. Nothing's due. This is just to show you. Remember, we had the midterm with calculation practice. And in that, there's the problems as well as the answers. And then there's also final calculation practice, problems as well as answers. And so those problems, like for instance, it'd be a good thing to just print out and have it work this as you're studying this weekend. Typical things we've been doing. Draw the contour map. What's the domain? Find the traces, sketch the surface. You guys have gotten really good at that by now. Getting gradients, remembering that the gradient actually points you in the direction of the maximum. It maximizes the directional derivative. So don't freak out when you see that phrasing, right? Directional derivative can go in any direction. They'll give you a vector they're interested in. And then if they were asking, what is of all of those 360 degrees that we could go around, there's infinitely many, directional derivatives. What's the directional derivative that maximizes the change in z? Well, that's just your gradient. We already knew that. That's our direction of steepest descent. What else? Okay, so we got partials, second partials. Yeah, more directional derivative practice. Finding your CPs and then determining with the d-tests. So definitely want those. Global extremely, you have those problems. Extreme values subject to constraints. We did those a couple ways. I can guarantee you there will be a Lagrange multiplier optimization problem on there. Some other optimization. It's long worded because I've done some of the work for you. Here's an optimization traditional way. Here's one where you can do it the traditional way. Find the point on the plane closest to a given point. And we've done some of those. I can, again, guarantee you there will be a problem. You have to show your work. And this one you actually have to do as a Lagrange multiplier. That's one that they want to make sure you guys know how to do that method. Okay, double integrals. We've talked about those on rectangular regions. Super easy in that case. Another double integral one. Okay, then we get into book 3.5, and we're doing all these things with, we can get angles, we can get lines through points in Rn, planes. What else do we, oh yeah, we took derivatives then of space curves. This is a space curve, and we could find tangent vectors, normal vectors. Some of those get nasty, right? So I might ask you to, it might be a very simple function, or if it's a more difficult function, I'll say use a tech tool to set it up. Here's the ones arc length and curvature can be nasty. I think this one, I think is doable by hand. I'm pretty sure I tried hard to find one. But I will have prompts on the final that'll tell you if it's, you know, just a nasty integral to jump to the tech tool. But yeah, surface areas, tangent planes, and then what we're doing in this chapter, gradient fields, flow lines, work integrals you're about to get to, curl, those things are the last couple topics. Okay, so please take a look at those, and let's go back. Notice also that there in this there is answers, right? So you can check them out. Very detailed, step-by-step work for each problem. All right, and then, so that's your final exam. One other thing I did want to mention is, I think I did this last week, but like, look, this is what y'all know. Like, boom, if you were to just like slap that down, like that's loud, right? That's how much material you guys know. It's in your head, it's in your bodies, it's in your brains. You're gonna ace this. So just look at it as an opportunity for you to show off. Not only did you learn all that material, Calc 1, 2, and 3, it's all at your disposal, is you did it in, particularly this semester, you did it in a self-directed learning environment. You did it during COVID, you did an asynchronous learning environment. So you really should, everybody pat yourselves on the back, congratulate your teammates, thank your teammates for helping you. Oh, that reminds me, what have you done for your team today? Think about that. Start a good thing to do. Decide if you're going to do this last challenge problem together as bonus. Decide if you're going to, or don't decide, just you should be making study guides together, getting that 2 pages of notes, because again, you have 2 hours. It is a time test. And so that'd be something to go through. Oh, I should have pointed out that when we had the screen share up, that final practice, I think that had twice as many problems as you're gonna have. So don't get alarmed if you can't do that one in 2 hours. It'll only have 10 to 15 calculation problems to be doing. Okay. Okay, so then let's go to the this week's assignments. The activities. So I agree, I think it was Liam said they were pretty conceptual and straightforward this week. I agree. Hopefully y'all felt that way too. It seemed as if you did. A couple folks I wanted to just mention a neat way for the matchings, the vector field matchings, to narrow things down. Some people used some of our vocabulary, like we had radial vector fields, rotational, and unit. And they used that last one, unit. That means every vector had to be the length 1 in the field. So they used that to narrow things down. I think that was Will and Liam did that. Then the vector field collection, this one was really interesting. Several people did this one. It was neat to see all the different. And so I'm just going to mention a few of them so that collectively as a class, we start thinking this way too. So Letheriel mentioned one of his was lattes being mixed. That's a vector field. He also thought about like aerodynamics of a car. And so often you see those shots of like a wind tunnel. And so you can imagine all those, they're really kind of showing flow lines usually in those, but that's another way of depicting what's in a vector field. Eleanor mentioned leaves blowing, and that got me thinking, like, actually you could think about just look outside at a tree, and every leaf is pointing in a different direction. Now the vector field isn't, obviously the tree is not uniformly spaced spots along those, but they don't have to be. Oh, which reminds me, someone was mentioning how many vectors they put in the field. Like, did they do too many? Oh, that was Olivia, right? I think was like, sorry, I might have put too many vectors in my vector field. Well, there's no rule. I mean, too many or too few. It's whatever helps you see the motion and the action of that field. And so, for instance, in a tree example, there's places where it's sparse, where like up the trunk, there aren't many leaves, and so it's not showing you much of the action down there. But once you get higher, then there's a lot more leaves. And so they don't have to be uniformly spaced. So a tree is a great example, which think of each leaf as a vector pointing as the wind's blowing in. But you want enough, so if you have to do something by hand, you want to put in enough so that you can see what's happening to the field, especially if you're given one algebraically explicitly and you want to plot it by hand without a tech tool. Right? With the tech tool, that's the easiest way to do it, right? To see what's happening as you rotate it. Who else? Oh, yes, Christy talked about, she had a life aquatic. So she grew up on the Gulf and then also did sailing. And she talked quite a bit and had some images in hers. I think I included in the samples and examples of different sailing terminology and how that related to vector fields. Griffin had one where he's talking about the air in the lungs. So as you're breathing, could be visualizing that as a vector field. Let's see, Kelly had like 30 some. It was crazy. One that was interesting was castle modes, like the fluid flow in a castle mode. Yeah, that could be considered. But there's a couple people did this too. Don't confuse space curves with vector fields, right? So the space curve, like this was one I liked too, of Kelly's. She had the flight of a flying squirrel. So if you're looking at the flight path, that's a space curve. So don't confuse space curves with vector fields. They are related, right? Because in a vector field, if you pick at one point that you want to start and follow the path of, let's do that, Eleanor's leaf blowing in the wind, well, that is following a particular path that's given. That path is a flow line, which is space curve. So motion of one particle in the field is a space curve, but the field itself is a vector field. Oh yeah, Grace is a meteorology major, so she was all about the weather vector fields. She had a ton of those. Oh, Patrick had a couple really cool ones. People migrating in Europe. So it took a map of Europe, and then we had these arrows of where people are moving, the motion of folks. Then he talked about static buildup, like if you ever in the winter gotten shocked, well, that particular point at which you're shocked, that static electricity was pointing to that. Boom. It's kind of like a little explosion, which gets me to the next one. He had quite a few examples with explosives and radiation blasts. He's in the military. And so I included his in the samples and examples because he had a cool link to a video you guys might like seeing. Gosh, what was it? It was a huge, like it looked like a cement truck or something that they're blowing up, an explosion, and they're showing, and it was a neat type of camera where it kind of showed it in waves and it would progress a little bit more, then stop and show. But anyway, as it's doing it, it's showing the radial blast from that. Perfect example and of a 3D vector field. And he had a couple more like that. So check out the video. I put it in samples and examples. And then Erin had a neat one with lava flow. I also put that one in. She also put Griffin's, Grant's, Clarissa, and Dana Mae, and Erin. They had some really nice explanations for the matchings and the flow lines. And in particular, I loved Erin's flow lines. She put several different flow lines in a vector field rather than just one little short one. She like really showed. It was very clear once the flow lines were in there to see what was happening. So check those out. And then in the gradients, the calculation section, I put Patrick Griffin and Kalersa. There wasn't many calculation ones this time, and this was page 252. You had to compute. So you were given an explicit function, and you had to compute the gradient vector field. And so that was something we had already done, but now we're looking at gradients as actually a vector field, right? Rather than our point, we can get them at all points, and we have this vector field. And of course, by design, they must be gradient fields. They have to have the potential function. You're getting the gradient. You actually got that from a function, an explicit function that was given, but well, that's your potential function. It wasn't hard to find. But there was a few questions on the answers on the other side. These were your steepest ascent. So there were questions about, well, how do I get the steepest descent? So a couple ways you could do it. Once on this side, you've explicitly calculated your gradient vector field. If you just negate, so you have a gradient vector field that's positive. If you just negate that, stick negatives in each component, in the partial with respect to x and the partial with respect to y. So you have the 2D vector field, right? That's what we're plotting on this thing, 2D R2 vector fields. If you negate each component, you get the negative gradient vector field. And you could have plotted that with the TeX tool and then use its flow line. So it has the flow line capability, clicking on a point and it'll show the flow line. Or the way I actually did it was just took the positive ones that were graphed, so I used a TeX tool to graph those. And then at any point, the positive one, so that's the one on the left here, I just follow the direction of the flow line. So I vector hop, right? I vector hop across, and I get to the direction, the path of steepest ascent. Now the path of steepest descent would just be starting at the same point and going in against the vectors in the field. So just go like that. That's how I drew that picture. So same thing here, right? I follow with I vector hop with the field, so moving in the direction of the vectors. And over here, I started at the same point and I just go against the field. Okay, so two ways of doing this. There are a couple questions on those. All right, I think that's everything for my notes. So last week, I'm getting ready for the final. And I just want to say, you guys are doing fantastic. You can do it. Continue to work to lift yourselves up as a team, and let's ace this final. All right, please shoot me more emails with questions. And if you want to do office hours, just let me know. Chloe and I are here to help you. All right, have a good week and good luck with all your classes. Take time to relax, stress. Go get those lattes and think of Ethereal's vector fields in them.